Welcome to the video lesson for Graphing Polynomials Part 2. Today we're going to take a lot of the things we've learned in this chapter and try and put it together to find the parts of our polynomials as well as describing our behaviors. To begin with, let's go ahead and look at our equation to talk about the end behavior. We can see that we have an odd positive function. Since we have an odd positive function, we know that on the left side it should be going down, so then our limit would say as x goes to negative infinity, f of x is going to go to negative infinity as well. And then on the right side, it should be going up. So we know that the limit as x goes to positive infinity is going to also be positive infinity. Again, because we have a positive odd function. To find our y-intercept, we're going to go ahead and plug in 0 for all of our x values. And notice that when you plug in a 0, this is going to become 0, this will be 0, this will be 0 as well, because it's all something times 0. So what we end up getting is f of 0 is 0 cubed minus 2 times 0 squared minus 4 times 0 plus 8. And again, the dominant behavior here is going to be this plus 8 because all these other terms are going to end up being 0. So I know now that f of 0 is going to equal 8. We'll move on to factoring. We're going to look at our polynomial here and kind of go through our general process. First off, do we have a GCF? Which we don't. Secondly, do we have 3 terms or 4 terms? If we have 3 terms, to do our butterfly method. If we have 4 terms, to do our factoring by grouping. And in this instance, we have 4 terms. So I'm going to go ahead and set this up to factor by grouping. We have our x cubed minus 2x squared. Again, we're going to group that. And then we have minus 4x plus 8. If we go through our steps for factoring by grouping here, we're going to take out our GCF, which is going to be an x squared here. That gets us x minus 2. And then we take out a negative 4, and we also get x minus 2 as well. Since I have those x minus 2's, I know that I'm definitely on the right track here, so I'm going to go ahead and factor out that GCF of an x minus 2. And then we're left with x squared minus 4. And then we can go one step further here, because I have x squared minus 4 is a difference of squares. We can factor that. We get x minus 2 and x plus 2. And then finally, because I see that I have 2 factors that are both x minus 2, I can go ahead and combine them. And this is where we see our multiplicity of 2 showing up. But we're going to end up getting x minus 2 squared, and then times x plus 2. Knowing that I have x minus 2 and x plus 2 as my factors, I can use that to help me set up my sign table with my x-intercepts. So I'm going to have values at negative 2, and at positive 2 for my x-intercepts. And now I have to determine what happens when I plug in some numbers that are in between and outside these values. So if I plug in a negative 3, I'm going to get negative 3 minus 2, which is negative 5 squared. That's positive. And then negative 3 plus 2 is a negative 1, which is negative. So I get a negative times a positive, which gives me a negative value. If I plug in, let's say I plug in 0, I already know that I get a positive 8, so I know this definitely is going to be a positive value. And then on the outside, if I plug in a 3, let's say, we get 3 minus 2, which is 1, and then 3 plus 2 is 5. So I know that I have a positive value times a positive value, giving me a positive value. And this supports the fact that we know that we have multiplicity of 2, so one of our zeros is going to be bouncing off. We're going to go ahead and attempt to graph this now. So again, I know that I have a 0 at negative 2. I know that I have a 0 at positive 2. And I know that I have a y-intercept at 8. At negative 2, the multiplicity is 1, so it should be crossing through. At positive 2, the multiplicity is even, so it should be bouncing off. And then if we're looking at our behaviors, I know that at the beginning we said that it's going to be going down on the left and up on the right. So all of these behaviors can kind of be tied together to make sure that we have a graph that follows through all of that. So I'm going to go through my intercepts, cross through, I know I have to bounce off here. And so we get something that generally looks like that. Again, going down on the left, going up on the right, crossing through at x equaling negative 2, and bouncing off at x equaling positive 2, again, because of our multiplicity. And then also making sure that we go through an intercept of 0, 8. Okay, we're going to go ahead and repeat that process for our next function. And I've modified it from the notes, so make sure you go and make that change. It's now negative x to the 4th minus 3x to the 3rd. And I did that because I wanted to space out our x-intercepts a little bit more what they initially were. Looking at my leading coefficient test, I know that I have a negative even function because it's negative and even. That tells me that on both sides it should be going down. So using our limit notation, we have the limit as x goes to negative infinity is going to be negative infinity, showing it goes down, negative right there. And then we have the limit as x goes to positive infinity is also going to be negative infinity. Again, we know it's going to be going down because we have a negative even function. We're going to go ahead and find the y-intercept. Again, we know we're plugging in 0 for x, so we're finding f of 0. I have negative 0 to the fourth minus 3 times 0 cubed. Similar to our last example, anything with a 0 in it's going to cancel out, and so we get that f of 0 is just 0. And that also helps us identify at least one of our x-intercepts, because if the y-intercept is 0, then the x-intercept by default also has to be at least at 0 as well. To find the rest of our x-intercepts, we're going to go ahead and factor this. Initially, we want to look for a GCF. I want to take out a negative x cubed, and I'm left with x plus 3. And this tells me that I'm going to have two x-intercepts, and both multiplicity that is going to be odd, and that helps me to identify it's going to be crossing through. Also, that I have one that is a cube, so we have that weird kind of cubic shape going through at that intercept. We're going to go ahead and use these values to help set up our sign table. So again, I know I'm going to have a 0 at negative 3. I'm going to have a 0 at 0 as well. And again, I know it's because I set my factors to equal to 0 to help me solve for that. All right, if I were to plug in some numbers for my sign table, let's say that I plug in a negative 4. Plugging in negative 4 into negative x cubed is going to make it positive. Plugging in negative 4 into x plus 3 is going to make it negative. So I have a positive times a negative, which means that I have a negative value there. If I were to plug in, let's say plugging in negative 1. If I plug in negative 1, this is going to be a positive. This is also going to be a positive. So now that I have a positive times a positive, which means that I'm going to have a positive function. And then lastly, if I plug in let's say I plug in a positive 1, this is going to be a negative. This is going to be a positive, giving me a negative times a positive, which is negative. So I now know the behavior of my graph at my zeros and in between, and then I know that has to be going down. We're going to go ahead and do some graphing here. I know that I have an x-intercept at 0. I know that I have an x-intercept at negative 3, and I know it has to be going down on both sides, so I can go ahead and start to sketch my function. Again, we know it's going to be going down. We also know that it has to cross through, and we know that at 0, we've got that cubic shape, so we want to make sure that we factor that in as well. I'm going to go ahead and zoom in just a little bit to graph this. Okay, so it's going to be going down on both sides. We also know it has to cross through it. We know we've got this general kind of cubic shape happening at our x equals 0. So we're going to cross through, come around, and then again, we know we have to kind of get that cubic shape at that x equals 0 because, you know, it's x to the third power. And now we have a general shape of our graph. Again, we don't know specifics. I don't know how high that relative maximum is. I just know that it has to turn at that point, and then it has to kind of curve through at x equals 0. Okay, so now it is your turn. Go ahead and try and fill out all the information for this function. Describe the end behavior, find the y-intercept, factor it, find the x-intercepts, create your sign table, and then use that to help you sketch your function. Go ahead and hit pause now, and then come back and check in and see how you did. Okay, so here we have our work. We can see that this is a positive odd function. So on the left, as the limit goes to negative infinity, we're going to be going to negative infinity. And then on the right, as x goes to positive infinity, we're going to be going to positive infinity as well. For our y-intercept, once again, we're plugging in 0 for our x values. Since all of our terms had an x in them, it's simplified to be just 0. And that does help us identify that one of our x-intercepts should also be 0. To find our x-intercepts, we factor completely. Start by taking a GCF, and then we factor the x squared plus 2x plus 1 to be x plus 1 times x plus 1, which leads us to x plus 1 squared, and that's important because we know the multiplicity is going to tell us that it bounces off at that 0. To finish solving for those actual zeros, I set the factors equal to 0, and I solved, and I got 0 and negative 1. For our sign table, looking at our two values again, we know that we have zeros at negative 1, we have zeros at 0. And then if we plug in values that are in between these ranges or on the outside, we see that on the left of negative 1, we get a negative times a positive, so the function is going to be negative. In between negative 1 and 0, we have a negative times a positive, so again, we're going to have a negative value. And then on the right side, we're going to have a positive times a positive, so then our function is going to be positive. And this tells us if we are going to be above or below our x-axis. When we go to sketch our graph, again, remembering that we have multiplicity of 2, that tells us that at -1 we have to bounce off, and then at 0 we can actually cross through. And this is our function, our sketch of our function. For this next part, we're going to talk about what happens when you have complex zeros. So to begin with, complex zeros always show up in conjugate pairs. And that's so that when we multiply them together, the complex portion will kind of cancel out. So there's always going to be an even number of complex roots. So this helps us when we're identifying the number of real zeros versus the number of imaginary zeros. So for all of our graphs below, we're going to go ahead and say that the overall degree is going to be 5, and that we have at least one real zero. And they're also going to assume that our leading coefficient is going to be positive to help us kind of identify what is happening here. When we look at this first diagram, I see that I only have one x-intercept, so I have one real zero. Knowing that our degree is 5, if I have one real zero, that means all of the remaining zeros have to be complex zeros, so then I have 4. And again, those would occur in conjugate pairs. When I look at my next example, I see that I have two x-intercepts, but when we look specifically at this x-intercept here, it bounces off, so that tells me that it has an even multiplicity. We'll go ahead and assume that that's 2 for this case. So I have 3 actual real zeros, again, because of the multiplicity, which tells me that I would have, again, 3 real zeros, and now only 2 complex zeros. Continuing on, we see that we have another function that's going to have 3 real zeros. This time it's 3 unique real zeros. They all have multiplicity of 1 because they're going to cross through. And once again, because our degree was 5, if there are 3 real zeros, that leaves us with 2 complex zeros. And then for the last couple of examples here, we notice that looking at our function, I have 2 zeros there, technically because of our multiplicity. So 2, and then 3, 4, and 5. So I actually have 5 real zeros, which means I have 0 complex zeros. And then looking at another example here, I have, again, 1, 2, 3, 4. I have 5 real zeros, so once again, we have 0 complex zeros. All right, that does it for our notes for today. Go ahead and get started on the homework, and good luck.